In this video, we'll be going through some more advanced integration techniques. So that includes longer synthetic division, trig identities, as well as completing the square. So sometimes it's not immediately obvious how we're going to integrate a function. So we're going to look at these three strategies to help us figure out some other methods we could use. So longer synthetic division can be used whenever the integrand is a fraction. Just recall from pre-calc that synthetic division is used when the denominator is in x plus or minus k format. So for example, it could be x plus 2 or x minus 4. And note, not all fractions are going to require division. Sometimes there are other things we could do, like looking for log or inverse trig antiderivatives. All right, if we look at the sample problem though, this is going to be one where we're going to divide, and I am able to divide synthetically because of the format of the denominator. So I'm going to rewrite this expression, putting some placeholders in that numerator, and then I'm going to set up synthetic division. So if the denominator is x minus 1, we're going to put a 1 outside the synthetic division format, and we're going to put in all of the coefficients in that top line. All right, when we synthetically divide, we're going to bring down the 6 and then multiply, add vertically, multiply, add vertically. And we end up getting, when we put our variables back in, 6x plus 6 over x minus 1. So we are basically integrating that new quotient. And when I do that, I'm going to get 6x squared over 2 plus 6x. And then for 6 over x minus 1, that's going to give us plus 6 ln of the absolute value of x minus 1 plus c. That's knowing your antiderivative rules from our previous video. And just know that if you thought maybe we could try power rule there, reverse power rule, that's really x minus 1 to the negative 1 power. If I had added 1 and divided by that number, I'd be dividing by 0, which we can't have. So just a note on that. All right, the next type is trig identities. So here are some trig identities on the left. Tangent is sine over cosine. Cotangent is cosine over sine. Then we have all of our reciprocal functions. We have our Pythagorean identity, sine squared plus cosine squared equals 1. And then sine 2 theta equals 2 sine theta cosine theta. All right, for our sample problem, we are going to be integrating cotangent of x, and that's going to need to be rewritten as the integral of cosine x over sine x dx. And I'm going to rewrite that one more time as cosine x times sine of x to the negative 1 dx. When I integrate that, I notice the derivative of the inner function sine x is sitting out front. So I know that I'm kind of doing reverse of chain rule here. So we have the same negative 1 exponent like we saw in the previous problem. So that's going to introduce natural log, this time of sine of x plus c. Our last example is completing the square. So that's used when a quadratic is not factorable. We take the b term, divide by 2, and square it in order to complete the square. And this often occurs in the denominator of a fraction and leads to inverse tangent or inverse cotangent as an antiderivative. So I'm going to rewrite the denominator in this sample problem here because x squared minus 8x plus 17 is not factorable. So I'm going to rewrite that as x squared minus 8x plus 16 when I take the b term, divide by 2, and square it. We're going to subtract out 16 because we don't want to change the value of the expression. And then we're going to put 17 back. So I'm going to rewrite that as x minus 4 squared plus 1 in the denominator. So x squared minus 8x plus 16, that's x minus 4 times x minus 4, which is why I'm rewriting it as x minus 4 squared. Now I can integrate this and realize that this is inverse tangent of x minus 4 plus c. All right, let's take a look at some other questions. Number 1 is a pretty good follow-up to that one because this is another completing the square example. So I'm just going to rewrite this so that the denominator is in standard form. Personally, I just prefer that in order to complete the square. So I'm going to now complete the square because it is not factorable. So I'm going to add plus 9 And then I'm going to put in a minus 9 plus 10 dx. I'm going to rewrite this as negative 1 over x plus 3 squared plus 1 dx. And now since we have the negative in the numerator here, I'm going to say that this is inverse cotangent of x plus 3 plus c. But just note that we could also have negative inverse tangent of x plus 3 plus c. Either of those two answers would technically work. Number 2, x squared minus 9 over x squared plus 1. So this is an example where I'm going to have to divide, but synthetic division does not work because of the format of the denominator. So I'm going to set up long division, and I'm going to, of course, put 0 in, or 0x in, as a placeholder. All right, so x squared goes into x squared one time. We're going to multiply that going around and subtract. And we basically get this remainder of negative 10. So that remainder is negative 10 over whatever we were dividing by. So in this case, over x squared plus 1. So our problem here is really asking us, okay, what's the integral of 1 plus negative 10 over x squared plus 1 dx? So let's integrate each part separately. The antiderivative of 1 is just x. Now I have the inverse cotangent again, so I'm going to say that this is plus 10 inverse cotangent of x squared plus 1 plus c. But just like we talked about in the last problem, you could technically make inverse tangent work here as long as we negate the value. That's because the antiderivatives for inverse tangent, inverse cotangent are just opposites from one another. They're derivatives, or opposites, I should say. So both of those answers would technically work for number 2. All right, for number 3, 2 sine x cosine x. We saw on the previous slide earlier in the video that this is equivalent to sine of 2x, which is a double angle formula. So I'm going to put a 2 here and a 1/2 here so that I can integrate easily. So I know that the derivative of the inside is 2, which is why I'm putting that 2 there, so I can see, oh, this is really the reverse of chain rule. We're going to bring down whatever's in front of the integral. The antiderivative of sine is negative cosine, and then plus c. And I'm just going to rewrite that, putting the negative in the front. So keep in mind, if this piece here that I'm circling, the derivative, the inner function, is already sitting there out front, that's your indicator that you can basically reverse chain rule. So normally we multiply by the derivative of the inside when we are deriving, but now we are just going to have that derivative sitting out front. Okay, number 4. Hopefully we're starting to be able to recognize those questions where we can complete the square in the denominator. So this is 4 over x squared minus 4x plus 4 minus 4 plus 5 dx. I'm going to rewrite that in the denominator as x minus 2 squared plus 1. And then my answer here is going to be 4 inverse tangent of x minus 2 plus c. And as mentioned, we could technically make inverse cotangent work in this one if that 4 becomes a negative. All right, for number 5, we definitely have a quotient here, but we actually do not need to use synthetic or long division because I realize that I can essentially rewrite that numerator as the difference of 2 squares, and that one of those squares is basically, or one of those factors is the same thing as the denominator. So I'm really integrating x plus 2 here, which is now a very simple integration problem, and that's going to give us x squared over 2 plus 2x plus c. Okay, for our last problem, we have cosine x plus sine x squared. So when we square something, we always multiply it by itself. And then what I'm going to do is I'm going to rewrite this one more time, basically distributing or using FOIL, however you want to think about it. And I happen to notice here that I have cosine squared x and sine squared x, or really plus sine squared x. And that we saw is one of those identities that is equal to 1. So this problem, number 6 here, has a lot of rewriting. And in fact, I'm not done with the rewriting. So I have now 1 plus 2 sine x cosine x, or you could have 2 sine x cosine x plus 1. That would be fine too. And then I start to realize something, and this is just coincidence in terms of this worksheet and this video, but we're going to have to integrate 2 sine cosine x, which we already did on number 3. If we look in the top left corner of the screen here, we integrated that. So I already know what that's going to be. So I know that my answer is going to be x minus 1/2 cosine 2x plus c. Now, of course, if number 3 did not exist here, we would have to repeat all of those steps. Rewrite 2 sine x cosine x as sine 2x using the double angle formula, and then integrate from there.